So hello everyone. So welcome to our this week Rogers Efficient AI seminar. Today we have the Professor Zheng from the UC Santa Barbara to give us this talk. And Professor Zhang is assistant professor of the EC department at UC Santa Barbara. And he also holds the joint appointments in the computer science and math department. He received his PhD degree in ECS from MIT, and his PhD dissertation received the ACM SIGDA Outstanding Dissertation Award and the MIT Dissertation Award. His research interests include uncertainty quantification and tensor computation with application to variation-aware electronic, botanic design automation, algorithm, and software-hardware co-design for high-dimensional and robust safe machine learning system. And Professor Zhang have received 3 best paper awards from the IEEE transactions. Recent academic recognitions include the NSF Career Award and the ACM SIGDA Outstanding New Factor Award in 2021. So now let's welcome Zheng to give us this talk.
Okay, thanks both for the host and for inviting me to giving this seminar. I noticed that there are a lot of exciting talks in this seminar series. Actually, I watched a lot of them on the YouTube. And today I will talk about some of the recent work in our group. Is about the tensor computation to improve the training on the edge device. And our main focus to develop memory and energy efficient training framework, because on the edge device, we only have very limited hardware resource. So here, first I would like to clarify that I changed the title a little bit. I changed from algorithm to hardware from algorithm to preliminary hardware. Because this project is still in so far, our result on the hardware part is still in the preliminary stage, and we expect to see more. And then I would like to acknowledge the contribution of my students, Cole Hawkins. He's a PhD student in the math department. He developed the theoretical and algorithm framework in this research. And actually, he will be on the job market next year. And then my former PhD student, Zhang, he worked on the FPGA part a lot. And then I'd like to thank Professor Cheng Hao from Georgia Tech. She's an FPGA expert. All of us know about her, and she collaborated with us closely on the FPGA part. Okay, and we all know that in the past decade, so basically deep learning kind of models have surpassed other kind of machine learning models in many applications, such as computer vision, speech recognition, and recently they have even achieved successful results in the scientific computing, such as for solving numerical PDEs. And if you look at the framework and theory of deep learning, it's basically the framework and the theory have been investigated a lot many years ago. And the recent access is mainly triggered by 2 factors. First factor is a huge amount of available data caused by for instance, such as the smartphones and by the internet and social networks. And the second main factor is the increasing computing power that can support the training of very large scale deep learning models. Okay, so if you look at some of the modernized deep learning models, they have a lot of model parameters, right? For instance, from hundreds of millions of bits in the AlexNet to the recent to hundreds of billions of parameters in the recent GPT-3 models. Okay, and because the growing size of deep learning models, the success of deep learning model also requires a lot of computing power. So this plot shows the increase of the computing requirement in the modernized deep learning models. We can see that since 2012 is basically a starting point when people show the superior performance of the deep learning with a lot of GPU training on the image task. And since 2012, we have seen that actually computing power for training deep learning models have been doubled, almost 3.4 months. Okay, this is the research result from the OpenAI, and this kind of increase not only brings in the complexity in the training, but also it also causes a lot of environmental impact. This has been actually increasing more and more concerns. A well-known study is actually is developed by the University of Massachusetts Amherst, and they have shown that actually when we train the modernized natural language process models, actually the carbon emissions actually can be much more than that in the flight and also in the vehicles. For instance, if you compare the carbon emission caused by the training of the transformer with the average US car in the United States, we can find out that actually the former consumed actually about 5 times more energy than the average US car in their lifetime. Okay, and if you compare with the flight from New York to San Francisco, actually we can find actually the gap is even larger, right? This is actually very surprising. Okay, because of the huge cost of computing power, and actually, if you look at the mainstream AI system, the main AI system basically is like this. Firstly, we have the data, and then we do the large-scale training on the cloud and on the HPC. So this requires a lot of hardware resource and costs a lot of the energy cost, right? And then after we train the large model, we do some post-processing, such as pruning, quantization, noise distillation, and then to produce some tiny or compact machine learning model, and then we deploy them on the edge device. Okay, this is the mainstream ecosystem. So in my talk, I'd like to rethink this mainstream AI ecosystem. Okay, if you look at this ecosystem, to do training to produce a huge model, because the huge model has much stronger express power. And then we do a processing to produce tiny models for the deployment on the edge device. So the question is, the problem to do the full-size training it requires a lot of hardware resource. And this is actually not possible if we have only the hardware resource on the embedded systems. Okay, so the fundamental question is, can we, for instance, skip the full-size training, generate a tiny machine learning model from the data? Okay, so one-shot training. Okay, the one-shot training should be done with limited memory, with limited computing hardware resource, and with very.
可能吗？
不是
啊？
睡得不舒服，换个姿势。我撒尿去。
Excuse me? Hello?
Hello, I can hear you.
Okay. I saw someone may have questions. Okay. And actually, in the recent years, there have been an increasing interest in the on-device training. There are many increasing motivations. One motivation is in the energy efficient training in some IoT devices. They have the sensor on the edge node, and they may want to directly process the sensory data to do the training. And another motivation is data privacy. So we know that there have been increasing concern about this in Facebook and Amazon, right? So, and if you look at, there have been a lot of social media. There have been a lot of the social network app, for instance, on our smartphones, right? And many of the users even don't want to disclose that data, right? So a strategy is that, okay, we for instance, the provider train some deep large scale models on the cloud, and then after the user downloads the app to the smartphone, and then they may further customize the app based on the personalized data, right? So they may want to do some conditional training on the edge device. And another increasing interest is not from the image or speech, it's from the control and the verification. So if you look at the autonomous system and autonomous driving, the image recognition actually is just one tiny component in the whole system. And if you look at the whole system, there are a lot of challenging tasks about verification and optimal control. The REFAI, we need to ensure that is a very challenging non-linear high-dimensional problems. And recently, machine learning shown actually so the control innovation to machine learning, and they need to solve the problem actually in the real time with very limited hardware resource. That is also one of the application scenario for the on-device training. Okay. So firstly, I would like to describe where our methods stand compared with other kind of on-device trainings. So I think right now there are two mainstream methods for the on-device training. The first one is distributed training, which is also called federated learning. Okay. So the key idea is that if we have large-scale training tasks, we allocate the training task to many edge nodes, right? And then we solve the subtask on each node. And this kind of method uses a lot of edge devices to do the training, and the bottleneck that they need to increase the communication cost. They don't reduce overall cost, and they just allocate the task to many devices. And another method is low precision training. Okay, so low precision training reduce the number of bits that are used to represent the training variables. So using this kind of idea, we can reduce memory consumption and also reduce training cost. IBM Research Lab has done a lot of interesting works in this direction. And in the recent results, they have trained some deep learning models with 4 binary bits. And this kind of method is applicable for both cloud and also for the edge device. The problem is that if you consider the low precision representation, actually the reduction of the memory is limited. For instance, even if you consider the reduction from the 32 bits to the recent 4 bits, and it's almost 8 times. Okay. So in our project, we consider the tensorized training can be regarded as a third dimension. Okay. So it can be combined with the low precision training and distributed training together. Okay. And this method actually allows us to reduce the training variables by several orders. Okay. Yeah, by several orders. And if you can reduce the training variable by several orders, actually we can significantly reduce memory and hardware resource. And then it is possible for us to deploy the training on the edge device. Okay. And in this talk, I will also talk a little bit about how to combine the tensorized training with low precision. But I think in the future, there will also be a lot of the co-exploration of these 3 components. Okay. Before I talk about our contribution, I would like to firstly show the high-level picture. And this high-level picture actually is used in many works. It's not only limited to our work. Okay. The key idea is to change the training variables by the low-rank tensor computation. Okay. So if you look at the training problems in the deep neural network, we have a lot of training parameters, such as the weight matrix, convolution factor, embedding tables. Embedding tables are used very often in the recommendation system and also in the later language process models. And also recently, attention layers have been used, for instance, in the transformer and GPT-3. Okay, and if you look at the training variables, a lot of the training variables they have a huge size. For instance, the weight matrix may have millions of model parameters. Okay, and then instead directly train the model parameters, we think about them from the high-dimensional perspective. For instance, for the weight matrix, we call the two-dimensional weight matrix to many blocks, and then we stack these blocks together as a three-dimensional or high-dimensional data array. And this kind of process is called folding. Okay, and by folding, we can get a high-dimensional data array, which is called a tensor. So here I show this figure just shows a three-dimensional tensor, but in practice, we can have even 5-dimensional, 10-dimensional, 20-dimensional tensor. Okay, and this process just change the data format, but does not reduce the memory. Okay, and the memory is reduced actually by a key concept, by a key step called the low-rank tensor factorization. So the low-rank tensor factorization is very similar to the principal component analysis or singular value decomposition on the matrix. So specifically, we can use different kind of low-rank tensor format, such as CPU format, target format, or tensor tree format. The key idea is that we don't need to directly represent the original tensor. Instead, we may use some low-rank factors, such as for instance, in the CPU format, the low-rank factors can be just some rank one tensors constructed by some vectors. Okay. By using this kind of low-rank tensor representation, and we only need to compute the tensor factors, and the tensor factors actually can hugely reduce the training variables. Okay. So for instance, in the original training problems, we may have millions or billions of training variables, and because a huge amount of training variables in the original training, we may only do it on the HPC or on the cloud. But now, if you consider the low-rank tensor factors, actually we have changed the training variables. Now we may reduce the training variables to a few thousands, right? And then if you have only a few thousand training variables, and then it is very likely that we can do the training on the edge device. Okay, so how does this method work? So here I show an intuitive example, to give a very simple explanation. So here we consider, for instance, a weight matrix with a lot of redundancy. Okay, this is a very special case, but it's enough to show the concept. So for instance, if you consider that a matrix over 1024 rows and 1024 columns, and all of the elements are 1. Okay, so definitely this matrix has a lot of redundancy. And we know that this matrix actually is the rank 1 matrix, right? So if you use a singular value decomposition, we can compactly represent this matrix as a product of column vector and the row vector. Okay, using the SVD, we can reduce the number of variables from 1 million to about 2,000. Okay, so if you think about this problem from the 2D matrix operation perspective, that is basically the best comparison we can take. But now, if you look at this problem from the high-dimensional perspective, actually we can do a much better job. So especially, we can also fold this data array, two-dimensional data array, to 20 dimensions, right? And for every dimension, the size is 2. Okay, this is a 20-dimensional tensor. Now, if you look at the 20-dimensional tensor, we can do a low-rank, rank 1 CP decomposition. Especially this high-dimensional data array can be represented as the outer product of 20 variables, and each variable only has 2 elements. Or each vector only has 2 elements. Okay, so now if you look at the tensor representation, actually we only need actually 40 elements. Okay, compared with the original 1 million elements, actually we have obtained reduction ratio about 26,000 times. Okay. So this kind of idea actually have been explored in the deep learning community actually since 2015. Okay, they have been used for both the post-training compression and for the training. Okay, so here I just show a graph to use a graph to show the existing work and also compare our work with the existing results. Okay, so dependent on the goal and also how we do it mathematically, we have focused. And firstly, on the post-training compression, people have developed both fixed rank compression and rank adaptive compression. Okay. For instance, the CPU format is most suitable. For the CPU format, people often do the fixed rank compression because it's very difficult to find out the rank. For the type format, it is more flexible to control the rank, so people often use it to do the rank adaptive compression. And recently, people have also extended this framework to the training. So basically, they want to skip. So for such training, they want to directly use the tensor factorization in the training process to reduce the memory and the computing resource. And they have done it for the fixed rank training. And first, in the fixed rank training, they fixed the tensor rank, and then they compute the low rank factors in the training process. They have done this kind of training for different kind of tensor format, from CP, Tucker, tensor train, or even the block tensor. Okay, but the fundamental challenge is that, okay, if we do the fixed rank training, actually the problem is that we don't know what is a good tensor rank in the training process. So we need to do the many training runs. Okay, so this motivates us to do the rank adaptive training. Okay, we don't want to do the many training runs. We just want to do a one short training to get a result. In this direction, so far they have been very limited research results. And we started this project around 2017, and we got our first result in 2019, and in the recent 2 years, we get more results. So basically, this is the main content of this talk. Okay. So what's the main contribution in this talk? Actually, the main contribution is the one-shot training, include algorithm and hardware. We want to do one-shot training, but actually this is not an easy task for the tensorized training. Okay, why? Because the determination of the tensor rank actually is a very difficult problem in the training process. So here I use a simple example, for instance, CP factorization to show this problem, right? So for instance, in the problem setting, we may have a tensor to represent the training variables. Right. So if you have a d-dimensional tensor and we have n to the power d variables, okay, and we want to reduce the training variables using the low-rank tensor factorization. For instance, if we consider the CP factorization, we may have R rank components. Okay, each rank component is outer product of the vectors. Okay, so we can reduce the memory cost from n to the power d to actually a linear function of n and d. Okay, this is a great reduction. This is good, but the problem is that, okay, how should we decide the total number of runtime components, right? So if the rank is too small, then the correct solution, and then the model may have very low accuracy, right? And then if the rank is too large, and then we may have some memory and computing overhead, and also the model may also have the overfitting. Okay, and this is a very challenging task because this actually is the NPR problem. Exactly, there means the tensor rank is the NPR problem. So one may ask, okay, can we just get the tensor rank? Okay, for the CP, it might be possible, but for if you consider other formats such as Tucker, tensor train, and tensor train matrix format, actually the tensor rank is a multilinear tensor rank. It means, okay, actually the tensor rank is a vector. Okay, it has multidimensional vector. And if you want to determine the tensor rank, and then we need to search the tensor rank actually in high dimensional search space. And for every sample in this search space, we need to do the training. Okay. So if you consider the Tiger tensor train matrix format, we may need a huge amount of training runs. Okay. So basically, from the circle point of view, this is exactly determining the tensor rank that you have problem. So the existing methods, almost all the existing methods, they use a fixed rank training, right? And they just train the model for many times. Okay. This kind of method normally lead to very low accuracy and very long training time. So to solve this problem, actually we develop a Bayesian training framework of mathematic rank determination. Okay, and this framework actually was inspired by the Qibingdao's group, developed by Qibingdao's group. Qibingdao, the group in Japan, they develop a Bayesian framework for the tensor computation. Tensor computation basically is a linear problem for tensor. The neural network is a more complicated nonlinear problem. And our work is based on that. Okay, so this figure shows a high-level picture. Okay, so we don't know what should be a good tensor rank in the training process. Okay, so how we address this issue? Okay, so we develop a Bayesian framework. The key idea is as follows. Okay, so firstly, we initialize the training with an inaccurate tensor rank R prime. Okay, the R prime could be very large. Okay, it could be very large. It could be far away from the exact tensor rank. And then we design a prior distribution for the tensor rank. The prior distribution could reduce the tensor rank, could shrink the size of the tensor factor. Okay, and then combine this with the likelihood function of the neural network model. Okay, the likelihood function actually only depend on the model architecture and also depend on what kind of rank tensor factor we have. So basically, the likelihood function is determined. So if we combine the likelihood function and also the rank shrinking prior distribution together, actually, we need to achieve a trade-off and a good balance in the training process. So with the Bayes rule, so we can infer the actual rank R, and the actual rank R is often smaller than the initial guess. Okay, so basically from the Bayes rule, we will learn the actual tensor rank and also the hidden tensor factors describe the model parameters. Okay, so this kind of framework can achieve actually a huge reduction in the training process. So firstly, the first step, the initialization process actually can reduce. We find on large models such as deep learning computation system model, the initialization step can reduce the training variables by 2 or 3 orders of magnitude. Okay, and but the initial rank normally cause inaccurate results, right? But that problem can be addressed by the Bayesian estimation. Okay, and then in the Bayesian estimation, we learn the actual rank, and then in this step, we may also obtain 1 order of reduction. And this step actually just get further reduction and also boost the accuracy of the model. Here, I'd like to remark that the tensorized training, the performance is less impressive on CNN. That is because in CNN, the model parameters actually in the CNN actually every layer has very small size convolution filter, right? And it's harder to compress the small size convolution filter. And actually, the CNN actually already use some tensor operation. Actually, theoretically, it has been proved that CNN is equivalent to a hierarchical Tucker decomposition. So for CNN, if you consider CNN, actually, the reduction in the first step is not that significant, and it's mainly dominated by the reduction in the second step. Okay. So now if you look at this problem, so mathematically, we can describe this problem as a Bayes estimation, right? So here we have D is the training data, right? And then we want to estimate the estimate the model parameters capital theta. We want to estimate the model parameter capital theta. So here the capital theta actually has two parts. The first part we denote as a lowercase theta. It is actually the tensor factors, right? For instance, in the CP format, there are just some matrix, right? In the target format, it is a small size called tensor plus some factor matrices, right? And another component in the training variable is actually the hyperparameters that control the tensor rank. Okay. So from the base rule, we know that this posterior distribution is actually proportional to the joint density, right? The joint density has two parts. The black part is the likelihood function, right? Likelihood function. The likelihood function is very long, right? For instance, for the classification problem, if you use the cross entropy loss, and then the likelihood function is just a multinomial distribution, right? And then another part is the prior distribution, right? We need to design our prior distribution for the tensor factors. Here is the prior distribution. We have actually two stages for the prior distribution. The first stage is actually a distribution of the tensor factor condition on the hyperparameter lambda, right? Here, the lambda is used to control the tensor rank. And another part is actually the prior distribution for the hyperparameters, okay? So we got a question in the chat box. One student asked, okay, if we use the Bayesian tensor rank decomposition, the Bayesian tensor rank calculation, we have some, for instance, overhead. Okay. The answer is that, okay, normally, yes, because if you do the Bayesian training, we need to estimate the distribution. Estimating the distribution is more difficult than estimating just one variable, right? But the solution is, okay, if you do it actually smartly, actually we can greatly reduce the overhead to make it very efficient. Okay, I will explain later. So now if you look at this framework, there are three fundamental questions that we need to address, okay? The first question is, okay, how can we design the prior distribution to automatically determine the tensor rank, right? To change the tensor rank in process. The second question is actually related to the question asked by the student. So how can we do the training efficiently, all right? How can we come up with a posterior distribution, right? So if the reservation solver actually is not efficient enough, and then we may have a lot of the computational overhead. And the third question is, okay, how can we implement this framework on hardware, especially on the FPGA with very limited computer resource, right? So firstly, we answer the first question, how to design the prior quadratic tensor rank. Okay, so as I said, if you configure the CP decomposition, and then we need to have R rank one components, right? R is just an integer, right? Instead of searching the integers, actually we have a Bayesian model, right? We want to learn the tensor factor theta and also rank controlling parameter lambda actually from the data. So when we design the prior distribution, actually we have first two steps. So firstly, we design prior for the rank controlling parameter lambda. So here we specify, for instance, some log uniform or half Cauchy distribution. So in this case, lambda will have a distribution that are highly concentrated around there. Okay, so in this case, lambda will have a high probability to be there. Okay, its magnitude is all normally very small, right? And then we use lambda actually to control the magnitude of every column in the tensor factors. For instance, we may specify, for instance, we may post a Gaussian distribution for every column of the tensor factors, right? And we set the variance of every column as one component of lambda, right? For instance, if one element of lambda is very small, and then the variance of that column is also very small. And if you consider zero mean and control variance Gaussian distribution, and then if the variance is very small, and all of the elements will be very close to zero, and then one column actually will be, the whole column will be very close to zero, and then it can be removed. Right? For instance, this figure just shows a different kind of value for different elements in the vector lambda. Right? If one element, for instance, if the second element of lambda is very close to zero, and then the associated columns in the tensor vector is also very close to zero, and then that column that can be removed. Okay. Or the reduction in the training process. Okay, and then this figure, shows the whole graphical model, right? Show the whole graphical model. So we want to train the tensor that describe the model parameters, and the tensor is described by some low-rank tensor factors, right? And then the low-rank tensor factors are actually controlled by the rank controlling hyperparameters, right? The rank controlling hyperparameter has a sparsity inducing distribution, right? And that further controls the variance of each tensor factors. And this concept can also be generalized to other kind of tensor format. For instance, if you consider the target format, the target format has a cotensor, small size cotensor G, and also for every dimension we have factor matrices. And in this case, we just need to change this model a little bit, right? For instance, for the cotensor, we may just place a Gaussian price distribution of the cotensor, and then we can just change the size of the factor matrices for every dimension, right? But in this case, we need to use n vectors to control each factor matrix. Okay. So why we need n factor? Why we need n vectors for the hyperparameters? That is because in the target factorization, the rank of different factor matrices can be different, right? And also the zero columns, the index of the zero column can also be different. So basically, every hyperparameter vector actually just control one factor matrix. Okay. And this idea is also extended to the tensor chain. Okay, in the tensor chain, and the factor matrix, the factors are not matrices anymore. The factors are actually some lower dimensional tensors, such as three-dimensional tensors. So in this case, we are not controlling the columns. So instead, we are just controlling the slice of the tensor chain factors, right? For instance, if you look at one hyperparameter vector, right? If one component of the hyperparameter vector is very small, and then a total slice of the tensor chain factor will be close to zero, and that total slice can be reduced, right? And then in this case, we will have a smaller size. We have a smaller size three-dimensional tensor. Okay, and the second question is, how can we do the training? Okay, so if we directly use the existing Bayesian solver to do the training, and actually we indeed have a lot of computational overhead. For instance, if you use some sampling-based solver, such as Markov-Chain Monte Carlo or Hamiltonian Monte Carlo, and then we may need to store thousands of millions of copies of the model parameters, right? And that is totally beyond the hardware capacity. And in Qibingzhao's paper published in 2015, they developed a mean field inference solver. But that kind of method is developed for the tensor compilation, which is much easier than the neural network training. And in the tensor compilation, actually we can derive a closed form update based on the expectation maximization process. But that kind of closed form update actually does not work for the neural network training. Okay, so to solve this problem, actually we need to think about it from the variational inference perspective. right? So we want to estimate the posterior of the tensor factors and also the hyperparameters, right? So to estimate the posterior distribution, we want to construct another density function Q that is very close to the exact posterior density, right? We can transform this problem to an optimization problem. For instance, we may want to minimize a distance. Here, the distance can be, for instance, K divergence, or can also be the Wasserstein distance or something like that, right? We want to minimize error between the between our construct density and also the exact density. And of course, there can be many choices the density function construction, right? And one possible solution is actually to use kernel representation, right? For instance, we may parameterize the density function with some kernel function, right? And each kernel function depends on the particles theta j, right? So because the kernel function depends on the particle theta j, if we have m particles, and then the Bayesian inference problem can be transformed to the optimization problem that find the optimal particles. Okay, this idea actually was developed by the Chang Liu, Professor Chang Liu at UT Austin. Okay, so this is this figure actually from his paper shows the whole process. For instance, the red dashed line shows the exact posterior density, right? And then by tuning the value of the particle by our optimization process, and then we can also change the shape of the constructed function Q, right? And then finally, here Q is shown by the green color. So finally, the function Q actually get closer and closer to the exact density in the optimization process. Okay, so if you use this framework to do the training, and then we only need to store for perhaps for instance 20 to 30 copies of the tensor factors in the training process, and then we have used this method to train some CNN and ResNet. Okay, so here this figure shows how this method actually determines the tensor rank in the training process. So for instance, if you consider the tensor training representation for the convolution filter and for the phonic connect layers, the green bar shows the initial rank set by the users, right? The initial rank is followed from the actual rank. And then the red bar shows the learned tensor rank in the training process, right? We can see that, okay, the tensor rank for different dimension can be entirely different, okay? But the key is that, okay, by using this kind of Bayesian framework, we can learn the tensor rank in the training process automatically. Okay, so is that the best solution we can obtain? Actually, no, right? So if you look at the Stein version of inference, we still need to use some particles to represent the posterior distribution, right? So actually, normally the total number of particles m is in the range of, for instance, 20 to 50. Okay. So can we use also further less variable to represent the posterior distribution? The answer is yes. For instance, and here we develop another version of inference solver based on the stochastic version of inference. So here we also use a mean field approximation, right? We assume that the posterior density can be represented as a product of the mass density of each group of variable. If consider the CPF map, yeah, right? In the CPF map, the training variables you have the factor matrices plus hyperparameters, right? So we can write the posterior distribution as a product of the distribution of every CP factor and plus hyper, right? And then we further simplify each marginal distribution as a Gaussian distribution, right? And then in this case, we just need to compute the posterior mean and the variance for each group of variables, right? And then we can solve the problem with stochastic descent. But if you directly gradient descent, the problem is that we have a gradient explosion because we find that actually the gradient of the tensor factor actually is inverse proportional to the rank controlling parameter, right? To overcome this issue, actually, we develop a hybrid update process. So firstly, we simplify the posterior distribution of lambda as a data function, right? And then we use a hybrid update, we use a gradient update for the tensor factor and also closed form update for the hyperparameters. Okay, so here is the training result for different kind of benchmarks, and we consider small size problem to very large scale problem. For instance, for the deep learning recommendation system, we have about 4 billion for the training variables, right? For all of these kind of benchmarks, using this kind of rapid adaptive tensorized training, we only do the training once, and we get similar accuracy to the standard training. For some of the problems, we get slightly better accuracy. Of some problem, we get slightly worse accuracy, and we can get different kind of compression ratio. For CNN, compression ratio is about is normally 1 order, but for large models with large, for instance, embedding tables, then we can get thousands or tens of thousands of reduction ratio in the training process. Okay, this figure shows the results on the natural language processing, right? We compare with the fixed rank training. The fixed rank training actually need many training runs, okay? Need many training runs. Here we just do 1 training run. Doing 1 training run, we still get better. We still get a better conversion ratio and also better accuracy. And this is the result for the Facebook deep learning recommendation system, right? We can clearly see how does the compression come from, right? We get about 2,000 compression in the initialization, all right? And then about another 15 times reduction in the rapid simulation. And because this is the Bayesian framework, actually we can also use this kind of model to do the uncertain quantification, right? For instance, for some of the images, very difficult to tell what the classification result exactly is, right? And then in this case, we can estimate the, for instance, probability of different kind of possible outcome. For instance, for this figure, right, it is similar to both, is similar to 2, 3, or 7. We don't know which result it exactly is, right? And then we just give the probability of different possible. And for this kind of method, because it can greatly reduce the memory consumption, so actually this brings in a lot of new opportunities for the hardware design, right? Either on different kind of platforms. So in this framework, we mainly implement the algorithm on the FPGA, and we want to demonstrate its impact on the, for instance, on the edge device and on the embedded platform. And when we do the FPGA training, so here we just compute the maximum posterior point, right? So we didn't compute the full posterior density, but compute just 1 point estimation, right? And then we also use low precision tensor factors, okay? So we use low precision tensor factors. Specifically, we don't want to use the full precision representation for each tensor factor. We want to use some binary variables to have a quantized representation for each element in the tensor factors, right? This can save a lot of the hardware resource. And then we train this tensorized model with the stochastic rounding, and we use different kind of quantization scheme for different parts. So far, right now, it's still very naive implementation, and there are a lot of space to do the further optimization. So here, this is our FPGA prototype for the training, right? So the key idea is that, okay, because we can greatly reduce the memory calls in the training. So actually, we can store the training variable, which are the tensor factors, in the on-chip memory. Okay, we don't need to put them in the off-chip memory. If we can put the training variable in the on-chip memory, and then we can avoid a lot of the data movement and also avoid a lot of the memory access to significantly speed up the training process. Because this is the tensor operation, so we also design some specialized process element to do the tensor conduction in the forward and backward process. Okay. This implementation is still very new. It's still in the preliminary stage, and we have the result for the function MNIST dataset. It's a small dataset, but it showed actually the potential for large model. Okay, so if you look at the original model to do the first training, it will consume actually 15 million of bits on the FPGA, and that is beyond the actually the memory port of FPGA. if you use the rank adapted tensorized training, and then we can reduce by 43 times. And then if we further use the low precision tensorized training, and then we can get about further 7 times the reduction, right? And then we can just reduce the memory cost of the training variables to only 51K, right? This is actually far below. This is actually far below the memory capacity of the FPGA, right? And then the total reduction is about 300 times, right? By combining the rank adapted tensorized training with low precision representation, right? And then if you compare the full standard training on the embedded CPU, actually we have obtained 60 times the speed up, right? We have also obtained about 120 times the energy reduction, right? And we saw accuracy drop here, and the accuracy drop is not caused by the tensorization; it's caused by the low precision representation. So we still think that okay, there are still some improvement to do in the low precision part. Okay, so this is a summary. So we have seen increasing interest of the on-device training with limited hardware resource. So basically, in this talk, we develop a on-device training framework with tensor operation. It includes the Bayesian model for the automatic ranking simulation. It includes also scalable Bayesian inference solver to do the efficient training, right? And also includes the low precision tensorized training implemented on the FPGA to achieve the speed up and to achieve the energy reduction, right? We have seen a significant reduction of the training variables in the training process by using this kind of method. And then in our preliminary FPGA, we have also seen very good speed up and also energy reduction. And that's all. I think now I can take some questions.
Thank you, Zheng. Very excellent talk. So questions from the audience?
I actually have a quick question. Thanks for the great talk. First of all, very informative. So question is regarding the essentially how the low rank training from the beginning affects the number of epochs before the convergence when you're training. That's what I'm curious about. Yeah.
Very, very good question. So in this work, we have not investigated. We have not yet investigated the number of epochs of the tensorized training, but we noticed some work, some very nice results in others' work. So here, this is a result actually published in 2018 in China. They consider, of course, they are not considering the rank adapted training. They consider the fixed rank training, right? If they consider the fixed rank training, they find actually the low rank tensor parameterization actually can reduce the number of epochs in the training process. So if you look at this figure, right? So basically, the blue curve shows the number of epochs for the standard training, and the other curves shows different kind of low rank tensor path for the training. So basically, to achieve the similar laws and also similar prediction accuracy, the low rank tensor parameterization actually use much less training epochs. And of course, this is the result on the recurrent neural network, especially on the LSTM. So we don't know if this kind of result can be generalized to the general deep learning.
Cool. Thank you very much.
You're welcome. So any other questions?
I think there's one question in the chat box.
Yes. So should we ask a question? So will it be possible to actually train models in embedded systems? I think so. Yes. My answer is yes. Right. Of course, it depends on your model size, and also depends on how much a model can be compressed. Right. So if we if you consider very large model, right, such as the transformer and the GPT-3, right, it might be very difficult to train this kind of model on the embedded device, right? But if you consider some, for instance, recurrent neural network or some object detection models, right, and for useful in the autonomous system, right? If you also consider some deep learning models for the verification and control of the autonomous system, and for them actually, it is highly possible that we can train them on the embedded systems. Yeah, the key idea is that if you can reduce the training variables by for instance 100 times or 1,000 times, and then a lot of things can be done on the embedded systems, right?
Hi, I have one question about regarding your tensor neural network.
Yes.
For your tensor the optimization process, how you implement in the neural network? Or I'm guessing you take the neural network, deep learning neural network, the parameter, and then formulate the tensor, then do the tensor. Low rank tensor process, and then feed the parameter back to the network and test the result, or any other imputation method to have it done in your real applications?
Very nice question. So actually, in the optimization process, there are so basically on the high level, there are two kinds of implementation, right? One implementation is that, okay, after we come to the tensor, low rank tensor factor, and then we reconstruct the model, right? We reconstruct the model parameters such as weight matrix and the convolution filter, right? And then we do, for instance, forward and backward propagation. But that is not very efficient. The second method is actually better. So basically, we do the forward propagation and backward propagation directly using the low rank tensor factors, right? For instance, in this case, if you have low rank vectors, and then if you do the matrix vector multiply on the fully connected layers, and then the matrix vector multiply will become a tensor network compaction, right? So we don't need to do the original matrix vector multiply, right? And also, if you do the backward propagation, we don't compute the gradient with respect to the matrix, right? So instead, we just use a gradient from the previous layer to calculate the gradient with respect to each tensor factor. That can help reduce a lot of the computing flops and also the memory.
So when you do the training, so you do this your tensor process layer by layer, or you train the whole layer, whole network the one time.
We do the training the whole network one time.
Okay, then after you do the tensor computation, you apply the whole parameter together and do the compression, and then feed the after you do this the parameter feedback to the original network, then test the result, right?
Yes. So basically, we can tensorize the multiple layers simultaneously. We don't do it layer by layer. So if we have multiple layers, and then we can represent all of the layers by the low rank tensor factorization. Of course, each layer is represented by one tensor, right?
Yes.
Right?
Yes.
And then in the training process, we optimize all of the tensor factors simultaneously in the training process.
Okay, so you do this tensorized for the network. So you use the existing neural network, the deep learning neural network for initial tensorize, or you just run that deep learning network structure and randomly initialize all the parameter. Then you do the tensor optimization, or you just that's my question.
We use the existing deep learning architecture to do the tensorized training. Because if you just randomly generate the neural network, we don't know if the neural network will have good performance or not, right? Even for the standard training, right?
Okay.
Right? So we want to make sure that we have very good baseline model.
Okay. Makes sense. Thank you.
Hi, I have a question.
Okay. Thank you.
How about the cost of training time when using the Bayesian approach?
Okay. For the Bayesian approach, if you consider training time, so far I think we have, we still have some overhead, and the overhead is from the overhead actually is not from the training parameters in the training process, because if you use a stochastic variational inference and near field approximation, we only need to double the tensor factors, right? So that is not a big overhead. Right now, the overhead is caused by the gradient estimation, right? Because we are computing the posterior distribution, right? So in each iteration, based on the previous posterior distribution, and then we need to estimate the new gradient, we need to have a sampling process. That can cause some computational overhead. And but the key that if you want to get a very good runtime, and then we don't need to do the full Bayesian training. We just need to compute actually the maximum posterior point, and then we can bypass that part. And of course, the loss is that we cannot estimate the uncertainty, right? We cannot estimate uncertainty, and there's always a trade-off, right? The uncertainty quantification is not a free lunch, right? So we want to get the uncertainty estimation, and then we need to do the training, and then we will get some overhead in the training time. And then if you don't want to have the uncertainty estimation, we just do the maximum posterior point training, and then the training overhead actually is much less.
Okay, thank you.
Great questions, thank you.
Hi, Professor Zhang.
Yeah.
Thank you for your outstanding presentation. I have a question. How do you decide the hyperparameter lambda? As I know, lambda is a vector, so yes. I think each single number is associated to one column or one slice.
Yes.
So how do you make? How do you decide which column is sparse and which column is?
I see. Very, very nice question. So here this last result. So basically, so lambda has many elements, right? Many elements, right? Each scalar of a lambda actually control based on one column or one slice. So the key is that when we design the prior distribution, we assign the same distribution to all of the elements of lambda, right? For instance, we can assign a log uniform or half Cauchy distribution to all of the elements of lambda. But the trick is this, right? Lambda, this distribution is only a prior distribution, right? It will influence the actual value of lambda, but it will not decide the actual value of lambda, right? So to actually decide the actual value of lambda, we still need to consider the data, right? The training data. So basically, there's a battle between the training data and also the prior distribution, and then they will achieve good balance. And so finally, when they achieve good balance, and then some elements of lambda have very large magnitude, right? And then some of the elements of lambda become very small, right? And then those small values actually will help us to delete some of the columns or some of the slices. So is this clear for you?
Okay, thank you.
Yeah, thank you. Very nice
question. And I have another question.
Yeah, please.
I'm curious about the intermediate memory demand, because yes. I think in the tensor computation, you have for a single layer, you have like several multiplication. So if you multiply the input tensor with the first tensor call. So yeah. I have typed this computation in the chat box. So the output intermediate tensor will be one dimension more than the input tensor. Am I right?
Let me see.
Yeah. For let's take tensor train as an example.
Okay.
So as we say, so the output tensor is one dimension more than the input tensor. because you have the rank R1.
The output tensor, okay, the output tensor is basically determined actually by the BIOS vector, right? So finally, the result will be, if you consider for the fully connected layer, and then the final side is the side of the BIOS vector, right?
Yeah. I'm not curious about the final size. I'm curious about intermediate size. You have applied additional memory to save this intermediate tensor.
Yeah.
Yeah, I think this intermediate tensor is larger than the final output.
Yes, I think so. If you consider, I think it should be around R times the size of the BIOS vector. I think this actually I can show you some results. The previous study. The previous study may have already actually shown the memory cost. Let me see. Yes. For instance, if you look at the initial, the first paper published by the Scotech group, right? They showed the memory cost, right? In the forward pass and the backward pass, right?
Okay, I see. Thank you.
Yes, we can see that actually it's dominated by the side of the BIOS vector, right? The side of the BIOS vector is basically M or N, right? Right. And then it's also multiplied by R in the contraction in the forward pass, because when we do the tensor network contraction, there also always in the intermediary data, there's always a phase lag associated with the tensor rank, right? In the tensor network representation, right?
Okay, thank you.
Yeah.
Any other questions from the audience?
Sorry, I have a final question. How about the real flops reduction about the complex model? The real flops reduction, if you consider the map training, it is also similar to the existing results. It's also similar to the existing results, right? If you consider the flops for every apple, right? It's also similar to this result, right? So you look at the column of the second here. Okay, thank you. Yeah.
I think there's another question in the chat box.
I see. Let me see. Oh, there's a question asking, does the rank shrinking process carry out on chip or off chip? So in our current FPGA implementation is done on chip, because the rank shrinking is controlled by the hyperparameter lambda, and the lambda actually has only a very small amount of variables compared with the low rank tensor factors, right? So it can be handled on chip.
Hi, Professor Zhang. I have another question.
Yes.
Is there any approximation for the Bayesian approach instead of the original Bayesian approach to accelerate the training or inference?
Yes, there are some. Yes, there are some approximation. So let me show you. So depend on the Bayesian solver, right? We have definitely need some approximation. So the the standard, if you just want to calculate the exact distribution, maybe Markov Monte Carlo or Hamiltonian Monte Carlo, that is very expensive, right? So instead, if you solely use a variational inference, then we cannot arbitrarily choose the function Q to approximate the posterior distribution. So instead, we need to choose it from a functional class, right? We need to choose it from a functional class H, right? So dependent on different kind of this H actually specify what kind of approximation we will have, right? So for instance, if you use a same variational inference, and then here we need to approximate that with some kernel functions, right? This is the approximation process, right? So here the kernel function can be, for instance, some Gaussian kernel, right? Right. This is just one type of approximation, right? And then another more scalable one, basically the stochastic variational inference, we have another kind of approximation, right? So we approximate the posterior distribution as the product of the marginal posterior distribution of different training variables, right? So in practice, it's very likely that they might be coupled to each other, right? But here, in order to reduce the training cost, we just simplify this by the mean field approximation. We assume that okay, the posterior distribution of the different training variable, they are, for instance, they can be they are independent of each other. They can be written as a product form. Yeah. So indeed, there are some approximation different on what kind of approximation solver we use. Any question here?
So if there's
any other questions?
So if there's no other question from the audience, actually I have two kind of the high-level general questions for you.
Yes.
The first one is that so we know that the use of the tensor method for the deep neural compression has been studied for a while, right? And
yes.
So once talked with some of the theoretical researchers just in the tensor theory, and they're also interested in that. But one of them once asked me one question. So I like to listen to your input. So what he asked is that, so for example, so we, like in your slides show that, so we fold a fully connected layer. We a matrix and then make it to a tensor, high dimension, and then then what he asked is that, so from a perspective of value intuition, so why we want to make a naturally low dimensional object to a high dimensional and then decompose it?
Yes.
It's kind of the counter intuition.
Yeah.
This was the question.
So the actually the answer is this, right? So if you look at the two-dimensional data array, if you look at the compression such as the SVD, right, and then we're looking at the global, we are looking at the correlation or redundancy of the global picture, right? But actually, there are still some correlation in some local structure, right? So here just shows one example, right? So what does that mean? So if you use this simple example, consider this simple example, right? If you look at the SVD just consider the redundancy of the of the global picture, right? We decompose it to the product of two vectors, and that's all, right? But if you look at it locally, right? If you look at, for instance, the further look at the low rank tensor factor of the SVD, there's still some local correlation, right, of the vectors, right? So we can further do the compression, right? This is just one explanation, right? So actually, from the PD community, from the scientific computing community, when they studied the low-rank tensor factorization, especially the hierarchical Tucker factorization, actually it has a close relationship with the H matrix, right? And the H matrix is also actually low-rank approximation based on hierarchical and local approximation, right? For instance, if you look at a matrix, the full matrix might be full rank, right? But if you partition the full matrix to different blocks, right? And then many of the blocks might be approximated as a low rank approximation, right?
Yeah.
Yeah.
And another question that is, so based on your observations and your predictions, so right now, so what is the current remaining or the emerging unsolved problems if you want to further promote the tensorized methods for the efficient
I think if you can do the one-shot training, right? If you can do the automatic tensor rank determination, the training process, I think there are many opportunities, right, on different kind of platforms, right? On GPU, there can be, some GPU computing kernel can be developed, right, to accelerate the tensorized backward and forward propagation, right? Right. So right now, some people they do the GPU training, they just simply implement some numerical algorithm on GPU, but they have not yet developed the specialized low-rank tensor computation kernels, right? And also on the cloud, right? And how can we do this, for instance, in distributed form, right? How can we reduce the communication cost, right? And also on the other hardware, right? They can easily consider different kind of platforms, and then there can be many opportunities on different kind of platforms, right? For instance, on ASIC chip, on the FPGA, single FPGA, multiple FPGA, right? Actually, a lot of opportunities.
So, yes, definitely there are a lot of opportunities, but what is the current challenges and potential limitations?
I see. I think that one of the current challenge, from my point of view, one of the current challenge will be actually a better theoretical understanding of the optimization process for tensorized training. Because if you look at the optimization landscape of the standard neural training, actually right now there have been a lot of understanding, right? For instance, optimization landscape, right, and how the HD converge for the standard training, right? But for the tensorized training, and then the optimization landscape will be changed, right? Right. So, for instance, just one audience just asked the question, right? How many apples if you cause for the tensorized training, right? We have seen that, okay, you can reduce the number of apples for the LSTM training, right? But what will be the result for the general case, right? And also, how can we make it convert faster, and what is the theoretical guarantee, right? So that is actually an urgent task for me, I think.
Yeah. Thank you very much.
Yeah.
So, any other questions from the audience? Okay, so if no more questions, so let's thank again for Professor Zhang's very informative and very excellent talk, and also thank all the audience for you attending our this week's seminar talk, and to see you next week.
Thank you.
Thank you, Zhang. Thank you. Have a wonderful day.
Bye.
Bye.